Okay, so you need a little help with the Unit 4.1 quiz review. Let's take a look at this together. For number 1, it says, what if you've got two elements together forming a compound? That is the exact description of a combination reaction. Two elements are getting married and forming one product. In letter B, if you've got a compound and it's breaking down into elements, that is a decomposition reaction. There's one reactant and there are at least two products. So now we're actually going to predict the products of some of these reactions and identify what type they are. Well, if there is a plus sign before the arrow, that is an indicator that it has the same structure as letter A here. So that would be a combination reaction. So we can go through, and anything with a plus before the arrow is going to be a combination reaction. Things with one reactant will automatically be breaking down, and so those are decomposition reactions. So let's remember what we need to do for each. In a combination reaction, we've got to crisscross the charges of the elements. And in a decomposition reaction, it's easy, we split them apart, but then we have to think about Hofbrinkel, or the 7 diatomic elements. And only those elements get a number with them, the number 2. So since number 1, or letter A, is a combination reaction, that means we're going to crisscross the charges. Aluminum has a +3, fluorine has a -1, so this becomes AlF3. The state of matter for an ionic salt would be a solid. NiBr3, breaking down, breaks up into Ni and Br, and then we check Hofbrinkel, and Br is indeed in there, so it gets a 2. Nickel is a metal. On the periodic table, it is colored black, so that means it's a solid, and bromine is colored blue, so then it gets an L for liquid. I believe that was wrong on my answer key too. Letter C, lithium and chlorine are combining, so we've got to check charges. Lithium's a +1, chlorine's a -1, so that means that this is a solid ionic compound, just like letter A. Letter D, if aluminum and fluorine are breaking apart, check Hofbrinkel, and fluorine gets a 2. Aluminum is a solid metal, fluorine is a gas. Another decomposition reaction, lithium breaks apart from nitrogen. Nitrogen is a part of Hofbrinkel, so it gets a 2. Lithium is a solid metal, and nitrogen is a gas. We need to crisscross for the last one here. Calcium has a +2 charge, oxygen has a -2, so those cancel out. It's just CaO, and it gets an S because it is an ionic solid. For number 3, we're supposed to draw an energy diagram for a reaction, reaction A, and it says it takes 100 kilojoules per mole to break the bonds, and the heat of reaction, the energy released overall, is -50 kilojoules per mole. So if it's negative, we know that the shape is, it goes up and then it goes way down. That is an exothermic reaction. And I didn't really make this to scale here. I'm going to do a little bit of a better job. Perfect. So it says for this one, label everything, make the reactants general. A plus B makes product C. The activation energy is how much it takes to get to the top of the mountain. So in this case, it takes 100 kilojoules per mole of reactants. And then the difference between the reactants and the products is called the heat of reaction. And I'm going to write RXN for short. In this case, it's -50 kilojoules per mole. This reaction would definitely be exothermic. Again, because the product, C, is lower in energy. Remember, this is energy going up, up, and up over here. And so, energy. So since the reactants are higher than the product, That means that overall the reaction is releasing energy. The transition state is at the top. This is where the bonds are broken and new bonds are going to form. So we can also add a few extra labels here. Bonds are breaking to get to the top. And then down here, new bonds are forming. Compare the energy needed to break the bonds and the energy released in making new bonds. Which is greater? The energy released in making new bonds here, big arrow all the way down, that's bigger than this activation energy right here, where that's indicating how much energy it takes to break the bonds. Oops, now we're supposed to draw the reverse of the reaction. So I'm just going to draw the mirror image here. So now we're starting with C and we're forming A plus B for the products. And in the reverse, if we've got to go from all the way down to the top here, I've got to add 150. So this becomes 150 kilojoules per mole as the activation energy. And here the heat of reaction is always the opposite in the reverse reaction. So it would be positive 50 kilojoules per mole. So this reaction would be endothermic because overall the energy is increasing. There's energy absorbed. And then there's a question, which reaction is more likely to occur? And it's definitely the first one, because this one only takes 100 kilojoules per mole to break the bonds, while the other reaction takes 150. So reaction A is much more likely to occur. It says, explain the details of how the electrolyzer worked in class and make sure to include all of these different words. Well, let's remember what was going on. Inside we had water, but we had KOH dissolved in the water. And that was because we needed ions so that electricity would flow through the water. We plugged in the alligator clamps, which were attached to a power source we could plug into the wall, and we started running electricity through water. In that process, we were breaking the bonds between hydrogen and oxygen and rearranging them to form hydrogen and oxygen gas. The hydrogen started building up on the black electrode side, the negative electrode, and the oxygen started building up on the red side. And we could definitely see that there was a 2-to-1 ratio of hydrogen gas to oxygen. And that's because for every molecule of water, there are 2 hydrogens for every 1 oxygen. Then what we did was we took these gases that we got from the water molecule from splitting water, and we combined them within a fuel cell. That process released energy, and we used that energy to make the little propeller spin. So we said this was a cycle because, again, within the fuel cell, hydrogen and oxygen gas combined and made water. And this process releases energy. Last part of the table, it says, complete the table for the various types of engines. There are so many different ideas that you can write down in this table. I'm going to go to my answer key here because I already typed this up. So electric motors, the fuel that's used most often is when you're recharging the battery, that's from coal burning somewhere or some sort of fossil fuel, versus an internal combustion engine is using gasoline most of the time, and hydrogen powered fuel cells are using hydrogen. Again, it's not perfectly innocent because to split water, we're often using coal to use electricity to split that water, or we're using methane gas, which is another limited resource. So pros of each. An electric motor has no harmful emissions, no carbon dioxide, no pollutants. It's also very quiet. With an internal combustion engine, there's a larger range. You can drive really far before you have to refuel, and there are refueling stations conveniently everywhere. With a hydrogen-powered fuel cell, there are no harmful emissions, and there's also quick refueling. So it doesn't take a really long time like it does with an electric motor. That is one of the cons here. It takes a while to recharge, sometimes up to 8 hours, and still there's a limited range, so you have to recharge more often. The internal combustion engine, of course, has pollutants, which we're very concerned about, and fuel is a limited resource for these engines. With hydrogen-powered fuel cells, you need hydrogen, and the current methods, like we discussed, use fossil fuels, and they're very expensive. Again, you could have had lots of different answers for those. Those are just some